So here we are on day 2, and the last day we're going to meet in class. So I'm going to continue here. The last day we're going to meet in class. So what I found was that the homework for test 4, which is chapters 8 and 9, the due date and time is actually this Friday at 1 p.m. Did y'all see that? Because I want you to be able to take the test that day. So if you can get the homework done by 1 p.m., then you'll have time to take the test before 11:59 p.m. Okay? And then the any makeup tests y'all want to do, you can do any 2 of them that you need. And I've seen that people have already started taking them and improving their grade, and I've been putting those in the grade book, so that's great. Any of those you want to do, you can do by Monday the 4th of May at 11:59 p.m. And then our final is up right now, and some people have already taken it, but you can take that by 3 o'clock on Tuesday, May 5th. Are there any questions about dates and times and due dates before we get started? No? Okay. So here we go. Let's do a problem. This one is a 2 independent means from 9.2. And it says that data in weights, pounds of the contents of cans of diet soda versus the contents of the regular version of the soda is summarized at this table on the right. Assume there are 2 samples that are independent random samples selected from normally distributed populations. Do not assume the population standard deviations are equal, and then complete parts A through D. Okay, so right here it says test the claim that the contents of the diet soda have weights with means that are less than the means of the regular soda. So diet soda has an average weight less than regular soda, okay? And it's clear here that diet soda is population 1 and regular soda is population 2. So what type of test is this, y'all? Left-tailed, right-tailed, or two-tailed?
Two-tailed.
Two-tailed? Does it say less than or greater than somewhere?
No.
Is it left-tailed? It says less than.
It does say less than. Yeah, it says that diet soda weighs less than regular soda, so M1 is less than M2. So this is
there it is. Oh.
Yeah, this is a left tail test. So this is going to be equal and then less than. Okay, now this is one that we can go ahead and put into the calculator. So I'm going to go ahead and pull up my calculator. And I'm going to split my screen. Oops. I'm recording. Okay, so here we are. We're going to put this in the calculator, but this is a two sample T for mean test. So we're going to go to that calculator. 2 sample T for comparing means. Okay. So we need our first sample mean, our first sample standard deviation, and our first sample size. That's on our table over here. So that's the diet soda. The sample mean is 0.79462 for diet soda. The sample standard deviation for diet soda is 0.00439. The sample size is 22. Y'all see where I'm getting these numbers from the table? Nick, you see it? Okay. All right, now the second sample mean is the regular soda. That's going to be 0.81152. The second sample standard deviation is going to be 0.00759. and the 22 again for the sample size. And this is a 0.05 significance level, means a 0.95 confidence level, so that's right. Because our normal null hypothesis will be that the means are equal to each other or that their difference is 0, I'm going to leave a 0 there and not worry about that, and I'm going to continue. This is a t-test, and my t-statistic is looking like negative 9.04 so negative 9.040. And my p-value for this left-tailed test will be in the middle here. It's basically 0. My p-value is basically 0 here. And that means if my p-value is 0 and my significance level is 0.05, should I reject the null or should I fail to reject it? What do you think?
Reject.
I'm going to reject the null because the p-value is lower. And I would only reject the null if there is sufficient evidence to support the claim that the cans of diet soda have a mean weight less than the regular soda. Okay, now they also want to construct a confidence interval to support the hypothesis test, and this is a left-tail test. So I can't just read this lower and upper confidence and call myself good there. That's not going to work. I'm going to have to change my significance level. And I'm actually going to have to double my significance level to make a confidence interval for this one-tailed left-tailed test. So my new significance level is going to be 0.1, and my new confidence level is going to be 0.9. And that is giving me, again, two negative numbers on my confidence interval, a negative 0.020 and a negative 0.014. And 0 is not in that interval because the lower is a 0 and, I'm sorry, the lower is negative and the upper is negative, so 0 is not between these two numbers. It says, does the confidence interval support the conclusion? Well, we rejected the null, and the null was what the difference of these means is 0, but 0 is not in here. So yes, this does support our conclusion. Because the confidence interval contains only negative numbers, not 0. And if we're doing the diet soda minus the regular soda and the diet soda is less than the regular soda, then we should get a negative number. And that's what the confidence interval is showing us, okay? So, we done? Oh, it's because I'm on the last problem. I'm like, how can I go on? I'm on the last problem. So yeah, so we'll make sure that we did that, but I believe we did that right. So let's just go on to 56 and let's continue our journey through chapter 9 here. We're kind of going backwards in time back to 9.1 now. 9.1 is two independent proportions, right? And in 9.1, we're going to be using the calculator that is the, it's on the first page, but it's the second calculator on the first page. Notice the first page of the calculator is 1 and 2 proportion. And so here's my 1 proportion, and over here, this is my 2 proportion calculator. This is the one I'm going to be using for 9.1. Do you see that, Nick? You said you had a question on 9.1. Okay, so this is the calculator that you're going to use. Okay. All right. It says test the given claim and identify the null and the alternative hypothesis, find the p-value, state the conclusion, as well as the final conclusion that addresses the original claim. Okay. And then it says among 2,168 passenger cars of a particular region, 239 of them had only rear license plates, and 400 commercial trucks, 56 of them had only rear license plates. A reasonable hypothesis is that the commercial truck owners violate the laws requiring front and rear license plate at a higher rate than passenger cars. Use a 0.1 significance level to test the hypothesis that trucks violate at a higher rate than cars. Now you might be tempted to say, oh, they said higher, so this must be a right-tail test. But if you read down here, it says, identify the null hypothesis and let population 1 correspond to passenger cars. So they're being really tricky. If trucks are higher than passenger cars are less than trucks, and population 1 is the cars. So we're gonna have to say that P1, the proportion of cars, is less than P2, the proportion of trucks. So it's very important to read which one is population 1 and which one is population 2. So I think it's even worth annotating that let population 1 correspond to passenger cars. And you see how I kind of had to scroll around to find it. So you have to be really careful. Okay, so that means this is actually a left-tail test, okay? Because passenger cars are less than trucks. Okay. So that's going to be this one, left tail. And now I think we're ready to go ahead and put it in this calculator. So P1 is our cars. So we're going to do the number of cars with rear license plates only over the total number of cars. So that's going to be 239 over 2168. And then the N1 is our total number of cars. $2,168 cars. And then our P2 is going to be the number of trucks with the rear license plates only over the total number of trucks. So that's going to be 56 over 400. And our N2 is going to be 400 trucks. And this is a 0.1 significance level, means it's going to be a 90% confidence level. Questions? Okay. We don't need to worry about putting in the null hypothesis because the null hypothesis will always be the two proportions are equal or that their difference is 0. So we won't worry about that. We'll just find our test statistic. And our test statistic is a z-score in this case. It's going to be negative 1.72. And then our p-value is going to be, because this is a left tail test, it's going to be this one in the middle, and it's going to be negative, p-value should remember negative. This p-value is going to be 0.0432, or around to 3 decimal places, 0.043. Okay, so we're comparing the p-value to the significance level. In this case, the p-value is lower than the significance level. So we will reject the null hypothesis, and we will reject it because there is sufficient evidence to support the claim that trucks violate the law more than cars. So we will reject the null only because there is sufficient evidence to support the claim that truck owners violate laws at a higher rate than car owners. Okay, this is a left tail test again, and they want us now to come up with a supporting confidence interval. So what is our confidence level going to be for this confidence interval, guys?
The lower and the upper.
No, but I have to change my confidence interval.
That's right.
What am I going to change it to? 0.80? Yes, that's right. It's going to go from a significance level of 0.1 to a significance level of 0.2, which means my confidence level is going to become 0.80. And that's only because if it's a right or a left tail test. If it's a two tail test, you don't have to change anything. I'm going to change that. And I'm going to get my upper and lower confidence there. So my lower confidence is going to be, and be careful because notice they have like an observed difference. So don't put that in your confidence interval because I almost did. So this is my lower and my upper. So it's going to be negative, let's see, round to 4, negative 0.536, negative 0.0536. And my upper is going to be negative 0.0059.
Wouldn't that be 0.60?
This number right here, my upper, right?
Yeah.
I don't think so because they want me to round to 4 decimal places. So 1, 2, 3, 4, and then I've got a 1 after my 9.
Okay, I see. I'm bad about rounding.
But no, that's a good question. Mm-hmm. So I think it's 0.0059. Okay. All right. So then, because okay, so this does not contain 0, which that's my null hypothesis is that this difference is 0, but it doesn't contain 0. We also rejected the null. Because the confidence interval does not contain 0, there is a significant difference because 0 would not be a significant difference, but any other number would be significant. So there is a significant difference between the proportions. And then there is sufficient evidence to support the claim. Questions? So this actually did support our conclusion. So I wanted to do 55 as well. I think 55 is 8.4. Already? Everybody okay? Okay, so let's go on. Yeah, 55 is a chi-squared test for talking about a population standard deviation. And this is where we have to build our chi-squared number, okay? So let's do this one. So our calculator is going to be the chi-squared numbers calculator. It's right here. And right here in here, this is where I would build my test statistic. And your test statistic is going to be, let's see if I can annotate and type this. I might be able to do that. My chi-squared number, I'm going to call it x squared, is going to be my, it's going to be n minus 1, which is my degrees of freedom, times my sample standard deviation squared, or my sample variance, divided by, and all of this is on top of my fraction. And then I'm just going to divide that by my sigma squared. Now, how am I going to write sigma? I'm just going to write sigma because that's my my population standard deviation squared. Okay, and this sigma is my claim. Okay, so it's in our notes, but I just was kind of being quick, so I just want to get the formula down. Sigma is your population standard deviation. It's that O with the tail on it. And your S is your sample standard deviation. So you need both to build this thing, okay? So let's look and see what our numbers are going to be here. A simple random sample of 35 men from a normally distributed population results in a standard deviation of 10.6. So our N is 35. Oops. So our n is 35 here. I'm going to write these. I don't normally do this, but since I'm, I want to make a clear example. So our n here is 35. Y'all see that? Sample size 35. Okay, that standard deviation of 10.6, that's the sample standard deviation. So that's our S, is 10.6. And then our sigma, and I'm just going to write sigma if you'll indulge me. That's actually our claim. So we're going to have to find some kind of population standard deviation. Let's see. The normal range of pulse rates is typically between 60 and 100. And if the range rule of thumb is applied to the normal range, the result is a standard deviation of 10. And then it says use the sample results with a significance level of 0.05 to test the claim that the mean pulse rate of men have a standard deviation equal to 10. So they're saying our claim for the population is 10. So my sigma that they're giving me is 10. And that's all I need. So now I'm going to go and I'm going to build my chi-squared value or my test statistic. Okay. So I'm going to start with 35 minus 1. And so I just like to do that in my head and say that's going to be 34. And then my sample standard deviation is 10.6 squared, and then 10 squared, that's my sigma. Okay, so you can actually just replace with your numbers into here if you want. Now it's not going to be accurate until I put my degrees of freedom down here. And what are my degrees of freedom, guys? What's my degrees of freedom for this problem?
34.
Good. It's going to be 35 minus 1, or 34. And just for reference, I'm going to put my significance level 0.05. It's already there. And let's look at our claim, because that's very important. We're going to test the claim that men have a standard deviation equal to 10. Okay, equal. That's our claim. So what kind of test is this? Left tail, right tail, two-tail, guys? If the claim is that it's equal 10.
It's two-tailed.
Two-tailed.
Two-tailed. Very good. It's going to be a two-tailed, an equal or not equal claim. Okay, and my chi-squared value I got when I built it was right there, was 38.2024. So that's already rounded to 4, or 3, they want 3, 38.202. Okay, and my p-value, now that this is a two-tailed test, now if you have a left tail test, please read the p-value right here under your degrees of freedom. This is for a left tail test. Right under the degrees of freedom, see p-value left, and then p-value right under that. But if you've got a two-tailed test, then you need to pick the smaller of these two values. This is a two-tailed test, so my smaller of my two values is going to be 0.5686. Do you have questions about that? This is for two-tail, this is for left tail, this is for right tail. Two-tail, you pick the smaller of these two. Okay? So I'm going to pick the smaller of these two since this is two-tailed, 0.5686. Okay? Now, 0.5686 is bigger than 0.05, so we're going to fail to reject the null this time because the p-value is bigger. We do not reject. The p-value is greater than the significance level, which means we're not going to reject. And we would not reject because there is not evidence to warrant rejection. Insufficient evidence. Okay. Questions? Awesome. So then I wasn't going to go to 40. I was going to go to 53. Let's see. It's going to keep backing up. 54 is that's an 8.3 question. 53 is proportion question. Do you guys want to see 54 or 53 or both?
53 is fine.
Okay. They're pretty similar, but they have different different calculators, right? So if it's about a mean, remember we're going to do the one sample t for mean. So if your claim, oh, I better erase some stuff. So if your claim is about a mean, it's going to be the one sample t for mean. If it's about a one proportion, then you're going to go to the first page and use the first calculator on the first page. So in 53, we're going to use the one sample proportion test. And so this is a, okay, so this is a test about a proportion, I think. Let me read it and see. In a study of accuracy of fast food drive-through orders, one restaurant had 38 orders that was not accurate among 325 orders observed. Use a 0.1 significance level to test the claim that the rate of inaccuracy in orders is equal to 10%. So this is another what kind of test? Which one of these is going to contain my alternative hypothesis here?
The two-tailed.
It's two-tailed, it's D, right? Okay, let's go ahead and put it in this one proportion calculator. First, this P should be our P hat. Oops, escape. The escape button has always been my friend. Okay, so we're going to, why am I going all over the place and being crazy? Okay, so we're going to put one proportion, our sample proportion, in the first box. And our sample proportion is, because our claim is that it's not accurate 10% of the time, our sample proportion should be 38 over 325. So that's what I'm going to put, equals 38 over 325. Okay, that means my N, I'm putting it in the wrong calculator, aren't I, Liz?
Yeah.
Fixing to say that, yeah.
I was just saying, wait a minute, where did the other P come from?
Thank you, yeah. I'm sorry, I was going crazy there. Okay, so let me put my P, because I only have one P, so I didn't have enough stuff to fill those boxes. So my sample proportion for inaccurate is 38 over 325. And remember, guys, if you're doing your final or something and you end up typing the Gettysburg Address in one of these gray boxes, and you know, all you have to do is close this calculator, don't save it, and grab another one off of Brightspace, right? So if it doesn't seem to be working, you can do that. Again, if your computer explodes, you know, you should probably call 911 first. After that, you can call me. Okay, N is 325. Okay, and my significance level is 0.1, so my confidence level is what?
99.
Is it? My significance level is 0.10.
90.
0.90. And we do have a null hypothesis here. It's the null hypothesis is that we have a 10% population proportion, okay? So that 10% population proportion is not our significance level. They just happen to be equal. The 10% came from the claim, right? 0.1, okay? So here we go. So we should have our test statistic here under Z, 1.02, 1.02. And then the p-value, this is a two-tailed test, so my p-value is going to be down here. The last one, 0.309. And that p-value, 0.309, we're going to compare to our 0.1 significance level. Is the p-value greater or less than the significance level?
Greater.
It's greater, so we're going to fail to reject, aren't we? And we would fail to reject because there is not sufficient evidence to warrant rejection of the claim that it's equal to 0.10. Now it takes us down to street level and says, well, if you if there's evidence to suggest that 10% of the restaurant's orders are being inaccurate, is this acceptable? What do you guys think? Yes or no? Is 10% inaccurate orders acceptable for a restaurant? I don't think so either. Since there is not sufficient evidence to warrant rejection of the claim, so it's not. So I'm not going to pick D. C says, since there is not sufficient evidence to warrant to reject the claim that the rate of inaccurate orders is equal to 10, the restaurant should work to higher the rate. To make the rate higher? That's weird. No, you know.
No.
Since there is not sufficient evidence to reject the claim that the rate of inaccurate orders is equal to 10%, it is plausible that it does have an inaccuracy rate of 10%. This rate is too high. The restaurant needs to lower the rate. Okay. Yep. Okay, so that was number 53. That was an 8.4 question. And I thought I would go to 51. I just kind of looked over. We probably won't get through all the questions that I wanted to do, but so 51 is a confidence interval of looks like proportions. Says that a drug is used to help prevent blood clots in certain patients. In a clinical trial, 4,331 patients treated with the drug, 120 of them developed the adverse reaction of nausea. Construct a 99% confidence interval for the proportion. So that's right there. That's a 1 proportion confidence interval with a 99% confidence level. To find the population proportion of people that get nausea. Okay, so this is like a 7.1 question here. So now we're in chapter 7. And 7.1 was proportions.
It was a what?
I'm sorry?
It was a what type of question?
From 7.1. It's a confidence interval about a proportion. So we're going to use, again, the 1 proportion calculator on the first page here, just to get a confidence interval. It's not a test this time. We're just trying to estimate the population proportion. We're not testing a hypothesis here. We're just trying to estimate the population proportion of people who experience nausea. Okay, so we still need our sample proportion. I don't know, I'm being careless with this calculator here. Okay, we still need our sample proportion. And if of the sample, 120 people developed nausea out of 4,331. And that is our N is 4,331. And this is 99% confidence level, so I put that in there, 0.99. And that's all I need. I don't have to worry about my null hypothesis because there's not one. My upper and lower are right here. So it's, let's see, we do want the best point estimate for the population proportion. Remember, that is our sample proportion right here on top. It rounds to 3 decimal places, 0.028. See where I got that? It's about 3%. And then my margin of error is right here. E is margin of error is 0.006. Margin of error is E. Stop me if you get confused. Okay. And then my confidence interval should be here. Lower confidence, upper confidence. So we're saying that we're 99% confident that the population proportion is between 0.021 and 0.034. And then what and there's only one correct way to interpret this, which is that we have 99% confidence in the interval itself, that it actually contains the population proportion. So one has 99% confidence that the interval from the lower to the upper bound actually does contain the value of the population proportion. We don't know what that is, but we are 99% confident it's between those two numbers. And then, I guess that was it for that one. Okay. This was number 51, and then I thought, let's go to 49. Oops, 52. 51. 49. Okay. This one is actually, now we're in chapter 6. Okay, so we're in chapter 6 now. We're going to be talking about the central limit theorem, and we're going to be practicing with our normal curve and our norm.dist and norm.inverse. Okay. This one says, assume that females have pulse rates that are normally distributed with a mean of 76 beats per minute and a standard deviation of 12.5. And then part A says one adult female is randomly selected. Find the probability that her pulse rate is less than 80. So this is actually a 6.2 question, and I would draw a picture. And I would draw a picture of a normal curve. So let me pause recording for doing it. Okay, so I'm recording now. We're going to draw a normal curve because this says that pulse rates of females are normally distributed. So here's my bell-shaped curve. Normally distributed pulse rates with a mean of 76. So 76 is right in the middle. Why I'm not using my stylus is beyond me. Okay. And it says if one adult is randomly selected, find the probability that her pulse rate is less than 80. So 80 would be over here to the right. 80, that's an 80, guys. And would I shade to the left or right, guys? If her pulse rate is less than 80, we want to find that area.
Left.
To the left.
Yeah, shade to the left. That's correct. We're going to shade all to the left, and we're going to find that area, which is the same as that probability, just for one person, just for one person. So all we have to do is, are we going to use norm.dist or norm.inverse?
Norm.inverse.
Nope.
Oh.
Norm.inverse is when
It's
you're
the other
given
way.
an area.
The other way. Yeah.
Yeah. Norm.inverse is when you're given an area and you want to find the data point. If you're given the data point and want to find the area, which is what we want here, we're going to use norm.dist. And it's going to give us the area to the left as long as we put in our x, which in this case is 80, and our mean is 76, and our standard deviation is 12.5. And this is cumulative because we're adding up the area. We're going to put a 1 right there, and we'll see that the probability is 0.6255. Questions? So to find the area in a normal curve, you're going to use norm.dist. If we wanted this unshaded area greater than 80, we could do 1 minus that and get that that area to the right. But we want the area to the left because it's less than. Okay. All right, now 4 adults are randomly selected. Find the probability that they have pulse rate with a mean less than 80. And if you remember, the central limit theorem says that there's a normal curve for these sample means. But we do have to change one thing if we're going to change to a distribution of sample means. We have to change one thing in our calculations. Anybody remember what it is? Has to do with the standard deviation. Now it's saying if 4 adult females are randomly selected, what's the probability that they have a mean less than 80? So 80 is still there, still shaded to the left, still got a mean of 76. But if you're dealing with means of a certain sample size, and you want to find the probability of a mean of a certain sample size, you're going to take the standard deviation, 12.5 in this case, and divide it by the square root of, oops,
Oh,
oops. You're going to take that and divide it by the square root of the sample size. So it's going to be divided by the square root of 4 or 2. But that you may have a number you don't know the square root. So just do square root of the sample size, just like that. And that number should get bigger. So you see how the only thing I changed, I divided by the standard deviation by the square root of the sample size, which tells me that any group of 4 females, there's going to be a 0.7389 probability that their mean pulse rate is greater than 80. Okay, questions? Now, the central limit theorem also says that this will work as long as your sample size is greater than 30 or your population is known to be normally distributed, or your sample is from a normally distributed population. And in this case, our sample size is not greater than 30. Our sample size is just 4. But it does say here that assume females have pulse rates that are normally distributed. So if we can assume that, then since the original population has a normal distribution, the distribution of sample means is normal for any sample size. Okay, so since it already stated that the population was normal, we can go ahead and proceed even if the sample size is not 30 or greater. Okay, this was central limit theorem, so that was 6.4. And then I wanted to look at a 6.3 question because remember 6.3 was a little challenging. 6.3 was where we first started to see sample statistics as estimating population proportions. And we determined that some sample statistics are unbiased or they target the population parameter, right? And they target it by if you put all of the possible sample statistics on a distribution, then the mean of that distribution will equal the population parameter. So I remember that this was challenging. It's always been challenging every semester. So y'all ready for one of these? All right. This one says there are 3 randomly selected households and the number of people in the household is 2, 3, and 10. Assume that the samples of n equals 2 are randomly selected with replacement from this population of 3 numbers here. When a sample, okay, when samples of n equals 2 are randomly selected, does the mean of the sample proportions equal the proportion of odd numbers in the population? So they are interested in the population of odd numbers. And that's important because if you don't get that, you can do all the math right and still get it wrong. You have to figure out what statistic they're after. And right here is the proportion of odd numbers in the samples and in the population itself. So the way we would do this is we would first, let's get our population down. And our population is just the 3 numbers, 2, 3, and 10. But each one needs its own box. 2, 3, and 10. That's our population. Those are the numbers in the hat, okay? And we're interested in the proportion of odd numbers. What is the proportion of odd numbers in this population, y'all?
Is it 1/3?
Yes. Y'all see that? Any questions there? We've got one odd number out of 3. So the population proportion of odd numbers is 1/3. Okay, let's see about the mean of our sample proportions for the proportions of odd numbers. So I'm going to copy these samples. I'm going to paste them over here. And there are 9 samples, and this is all the possible samples of size 2 from this little population of 3 numbers that I get. Now, what we want to do is we want to find the proportion of odd from each sample. Okay, so the first sample is 2, 2. What's the proportion of odd numbers in that sample?
0.
Good. What about in the sample 2, 3?
0.5.
Good. And here's another 0. Here's another 0.5. What about in the sample 3, 3? Odd
1.
numbers? 1, right? They're both odd. This one's 0.5. This one's 0. Looking for odd numbers. This one's 0.5. And this one is 0. So we only have 3 reoccurring proportions of odd numbers. You'll see that? So what we're going to do is we're going to make now a probability distribution with our unique proportion of odd numbers, which there's only 3 of them. I think I'll go ahead and scoot this over 1. We only have 0, 0.5, or 1. Those are our only choices. And now we're going to make our probability. If this becomes our new sample, what's the probability that we would pull out a 0? So there are, out of 9 numbers here, how many zeros do we have?
4.
4 ninths. And then we also, I think, have 4 that are 0.5. And we only have 1 that is, oh, this should not be a 5, that should be a 1. Sorry about that. But we only have 1 1 in there, right? That sample of 3 3. So that's going to be 1/9. And remember, this should add up to 1, and it will. It'll add up to 9 over 9. Okay, so remember that our population proportion of odd numbers was 1/3, and we're going to find the mean of our sample proportion of odd numbers. So let's go ahead and fill in this table. 0, 0.5, and 1. And they want fractions here, integer or fractions. So I'm going to put equals 4/9. Oops, I don't need an equal sign. That'll mess me up. Don't put equal. Don't do what I do. 4/9. And I'm going to put 4/9 again. And 1/9. Okay, so there's my probability distribution. And now let's find the mean of it so that we can compare the mean of my probability distribution with my population proportion of 1/3. Okay, so I'm going to do my proportion of odd times my probability. And just do that here. And pull it down. And to find the mean, I'm going to add it up. Add those products up. And there it is. There's my 0.333, same as my proportion of odd numbers in my population. This is my mean of sample, oops, proportions. Okay, mean of sample proportions is 1/3. So it is a good, it does target. Okay, it is a good estimator. So the proportion of odd numbers in the population is equal to the mean of the sample proportions. That's true. The sample proportions target the population proportion of odd numbers. And so the sample proportions make good estimators for population proportions, and that's always true. Wow, it's 2 o'clock. We can keep going until 2:20. Any questions? Thank you guys for sticking around. Hopefully this is helping. That was 48. And then I thought, let's look at 46. I kind of did every other problem here. So this is a good one. Let's see. Well, let's see what it is. We might have to draw a picture.
What chapter is this?
Let's see. Let me read it here. You guys, maybe you can tell me what chapter you think it is.
5?
Engineers, it does have a lot of percentages in it. I haven't read it all.
Chapter 4? No.
What?
I said chapter 4?
Chapter 4. Chapter 5 is binomials, remember?
Oh.
Oh, yeah.
Chapter 4 is percentages, but I see this P90 here. Let's see. Engineers want to design seats for commercial aircraft so that they are wide enough to fit 90% of all males. According to accommodating 100% would be too expensive. Okay. Males have hip breadths that are normally distributed with a mean of 14.8 and a standard deviation of 0.8. Find P90. Now, P90 is a hip breadth. And I'm going to say that a lot because I know that it's going to make Michaela laugh because of this. She just thinks that's funny that we're talking about hip breadth.
It's a weird word.
What?
It's a weird word.
It's a weird word. It's just weird. But you know, you have to have a seat big enough for your hips. That's all I'll say since I'm recording. Okay. So, yeah. So what do you guys think? It's talking about a normally distributed population. So maybe this is from chapter 6, right? From chapter 6, because it looks like we're going to need to draw a normal curve. And, ooh, I don't want it to be that big. Ooh, I still don't want it to be that thick. Let me pause recording for just a second. So we're going to draw a normal curve here. We're going to put our mean of 14.8 right in the middle. Sorry, but there's a 14.8, okay? And we want to find P90, and P90 is going to be the 90th percentile. So it's going to be, is P90, that's a hip breadth, where 90% of the data is less than. So is it going to be over on the left or the right of this curve, y'all?
Left.
It's going to be P90. So it's going to be a large hip breadth. 90% of people have less, narrower hips. So it's actually going to be over on the right. And it's a data point. It's not an area. It's the 90th percentile.
Oh, okay.
So if we're looking, but what we know, since this is the 90th percentile, what we know is that 0.90 is to the left of it. So we know the area to the left of it. We know the area. Forgive my annotating, it's gotten out of hand. But we know the area here, and we're looking for this data point down here. So how are we going to find that? What are we going to use? We're looking for a data point. We know that 90% is to the left of it. What are we going to use?
Is that the norm.inverse now?
Yeah, it is. You're right. So we're going to use equals norm.inverse. And the probability to the left will be 90.90. And the mean is going to be, they said 14.8. and the standard deviation is going to be 0.8, and that's all we need. Oops, 14.8.8. That's all we need, and that is our norm inverse, okay? So that should give us this, this data point here. In inches, it's going to be 15.8. 15.8 inches is the 90th percentile. Okay, questions? All right. Let's see, that was 46. So we're moving quite along here quite well. And we've still got some time. Let's see, what next? Let's look at, this would be similar. We would use norm inverse there. I was thinking about doing 44, but maybe we already did one like it. You guys tell me, what would you use to find, this says find the area of the shaded region. What would you use? Someone tell me what you'd use in Excel?
When do you use norm.dist?
Yes,
Or-
that's right.
yeah.
You'd use norm.dist. And it's to the left, so you would you could just put in just plain old norm.dist. Okay, let's go on. You guys need to see that one, or can we go on?
I would just do it just in case.
Just go ahead and do it. Okay. All right. So norm.dist. So we're going to do, because we're already given the data point, we're looking for the area to the left. So we're going to say equals norm.dist. And the area, okay, so x. So our x is 105. That's our data point. What is our mean here, y'all? What does it say our mean is?
100.
100. And our standard deviation?
15.
15. And we do need 1 for cumulative. That should give us our area to the left. And it's bigger than more than half. It's 0.6306. Michaela, can you see the dark shading on that one?
Yes, ma'am, it's dark enough.
Okay, good. 0.6306. Okay. Then let's see, 44. Okay, let's just keep going. Let's see, 43. Now this is an interesting one. I'm not looking forward to annotating it with my very thick pen, but I'm gonna give it a try.
I could probably annotate from my phone. I have a stylus.
You want to? Okay. This is not a normal distribution. This says that waiting times of subway departure waiting times between subway departure schedule and arrival of a passenger are uniformly distributed between 0 and 9 minutes. Now, uniform distribution is what shape, you guys? What shape should this distribution be?
Is it this rectangle?
It's a rectangle. So you want to draw a rectangle on our, you can just draw it right there on, like underneath the problem if you want to. Michaela, you want to try it? Oh, awesome. Okay, good. Okay, so there's our rectangular uniform distribution. And then can you put a 0 right down here on the left corner and a 9 on the right? Awesome. Okay. Now, find the probability that a randomly selected passenger has a waiting time greater than 4.25 minutes. So we need to eyeball where 4.25 would be, and it's greater. So we would shade to the right. So yeah, there you go. Awesome. And then you'd shade to the right. Good job. Should have had y'all annotating all along. Okay, great. So we want to find this area, and we don't need any special kind of function in Excel to find the area of a rectangle, because we know that the area of a uniform distribution is length times width, or length times height, correct? So let's figure this out. We need a length. We need a height. And then we need to find the area, and the area will be the same as the probability, just like in a normal curve, okay? So, so our length should be fairly easy to find. The length of the shaded rectangle that Michaela drew, how do we find that?
Will it be the 9 minus 4.25?
Exactly so. Okay, and then how do we find that height? It's that this other dimension. So in that case, we're going to remember that the entire rectangle is 1 and that the entire length is 9. And so if 1 equals 9 times the height, then 1/9 is going to equal the height. So it's going to be 1, which is our total area, over our total length. So our height is going to be our total area, 1 rectangle, over our total length of 9. Y'all remember that?
Yeah.
Does it make sense? So any time you're doing one of these uniform distributions, to find the height or the width, just take 1 over the total length, okay? So then to find the area of a rectangle, we'll just multiply these. And there we have more than half, just like Michaela drew, 0.528. Questions?
Glad we did that one. I did not remember that.
Okay, does it make sense now?
Yeah. It's just if I would have done this, I'd be, whoa.
You
I don't
probably
remember.
would have tried to somehow put it in a normal curve. So,
Yeah.
so look carefully for that, the word, what kind of distribution it is. It might be binomial, it might be uniform, right? So, okay, that's actually also in chapter 6. It's like the beginning of 6. And a chapter 5 problem, 5.2 binomial distribution problems. So I wanted to remind you guys of the chapter 5 notes. So this is a binomial distribution. I know that because it's giving me a fixed number probability for success. And it says when adults with smartphones are randomly selected, 39% of them use them in meetings and classes. Also, this is binomial because either they use their cell phones or they don't. So there's 2 outcomes. And that you get a fixed number of trials and they're independent. So I know this is binomial. And this says find the probability that exactly 3 of them use their smartphones in class. So if you remember this page from chapter 5, point 2, it's got several examples on it. So this one is exactly X. So that's the one we're going to use. You also have fewer than X, and then you got the formula for that over here. You have at least X, which is the greater than or equal to, and then you have X or fewer, which is another example. But we're going to use the one that says exactly. And so the formula is right here. So let's put the numbers in. And the way we would do that is equals binom.dis. And then X, or S is our number of successes. That's going to be 3. And our number of trials is going to be 6. And our probability of success is going to be 0.39. And 0 because it says exactly. And there you have the probability of exactly 3 out of 6. 0.2693. Okay. Now let's see how much time we have. we're just about out of time. And we did get quite far. And like I said, I knew we weren't gonna get all of these done. So I think I will go ahead and stop here. But you guys are welcome to come and, especially if you try the review, I'd like for you to at least try it, and then you can ask me the ones that you're having trouble with, you know? I mean, I don't mind if you want to work on the review in the lab. That's fine. Yeah. So any questions?
Are you going to be available anytime tomorrow?
Yeah. Tomorrow's Friday. I'll be in the lab from 8 to 1. And if you need to, I can probably do like a 7 to 8 or something like that. Or if you just text me, like, I know we're kind of getting close to the end. If you want to get together over the weekend, you guys can just text me on my phone or email me. But texting would get me quicker. I really don't mind if you want to do that.
So the final is due on the 5th.
Yes. Like if you
But-
look at our syllabus, it's always been the 5th. That's Tuesday. That was the day we were going to take it. We're going to take it from 1 to 3. So it's up right now. It's ready for you whenever you're ready to take it, as long as you're done by next Tuesday at 3 p.m.
Okay, and then but the is it the makeup tests are due on the 1st?
No, the 4th.
The 4th?
Right.
Oh, the
So
1st.
we've got 3 things going on, right? We've got test 4, which is due tomorrow before midnight.
Okay.
Then we've got possibility of 2 makeup tests if you need them. You don't have to take them unless you need them. But those, then take test 4, then your makeup tests are due by the end of the day on the 4th. Because the final is due by 3 o'clock on the 5th. Does that make sense?
Yes, ma'am.
And it is in an announcement, and I think the announcement is correct. One of the things that I thought was a little confusing about my announcement is I said that the homework and the test was due by midnight on the tomorrow, test 4 and the homework, but actually the homework due date is tomorrow at 1 p.m. So you can still work on the homework after 1 p.m., but it'll be 10% off. So if you can get your chapter 8 and chapter 9 homework done by 1 p.m. tomorrow, you won't have to take that 10% off of that. So, okay, does that make sense? You don't have to like it. Does it make sense? Are there any questions? Okay. All right. Well, if there are questions, you guys come see me. And again, we can set up something for the weekend if we need to, for Friday. Again, I'm in the lab till 6 tonight. In the lab until 8 to 1 on Friday, and then I'm available. Okay.
Okay.
All right.
Thank you so much.
Thank you.
You are welcome. I will see you guys back in the virtual math lab. I'm going to end the meeting.
All right. Thank you.
Bye. You're welcome.